Good afternoon, this is Schweitzer, and I am going to be doing a little video of the answer key here. Some things I'll be doing more into depth than others, but for the most part, you're kind of suggested to try a problem for the video for the answer. Not being able to translate this acid. That would be an oxyacid H2SO4. Alright, and I'm going to react this with lithium hydroxide, and then of course we have a cation and we have an anion, we have a cation and an anion, so that's going to be looking like a solubility reaction, but I don't personally mark that wrong on a test, but at least not at this point. But when we get HOH, we get water, and that's a specialized little version of this called a neutralization. So either solubility or neutralization. Alright, so next up we got this as a water, and you could even list this as HOH, which would be just fine as well. Plus, in this case, lithium sulfate, and technically you want to check this guy for solubility, +1 -2, that's why that 2 is there, and it turns out to be aqueous. Alright, aluminum acetate. We got Al parentheses C2H3O2, and then we got 3 right here, plus sodium metal. Right away I can say that this guy has no charge. Ionic compound, this is looking like a redox reaction. Alright, and then we get NaC2H3O2 plus, now aluminum has lost its charge and will be just simple metal. Balancing here will give me a 3 here and a 3 here. We do need, because it's a redox reaction, to check for oxidation states. Sorry, for voltages. And our voltages here are going to be 2.71, a -1.66, giving us a grand total of positive 1.05. Again, how do we get that? Well, this is going to be 1/2 reaction, right over there, and right there, and this guy is the other one. So at this point, it would be, if you are good at it, you could do it on the fly here, but you might want to sketch out the 2/2 reactions. Na metal going to Na plus. This is +1 electron, that's oxidation, and then aluminum +3 goes to aluminum metal +3 electrons. So this is going to get multiplied times 3, and that's where we get the 3 here, 3 there. But we have a voltage for this guy and a voltage for this guy. Careful on the reduction of potential chart. This is the one that's going to get flipped. Alright, and again, that's just a quick summary of how we get that particular value. If you have an issue with that, make sure you see your teacher or see another resource to figure that out. Alright, we got cobalt sulfide, that's COS plus nickel chloride. Again, that's going to be a 2 here because we got +2 -2 +2 -1. This is looking like a solubility reaction. Solubility. Alright, so charges will not be changing. Cobalt chloride +2 -1, and then plus nickel sulfide. Again, these are just potential products. We still have to check for solubilities to make sure that it's actually gonna, something new is gonna form. In this case, after checking the solubility charts, this is aqueous and this is a solid. Balancing here, it's already balanced. All right, we have ammonium silicate, NH4SiO2. Now that one I got off of my ion sheet, and if you aren't familiar with it, make sure you look it up. This is going to be potassium phosphate. All right, again, cation anion, plus 1 minus 2 plus 1 minus 3. This is a solubility reaction. Therefore, my potential products are ammonium, right? And this guy is going to be a 3 here, and it's going to be the phosphate. So recharge balancing your products. Probably one of the most common ways to lose points is not charge balancing things correctly. And we have potassium silicate, SiO3. And of course we get a 2 there, plus 1 minus 2. Now you can balance if you like, but this thing is going to be an aqueous and an aqueous. Due to the shortcut rule, this is aqueous and this is aqueous. So this is going to be a no reaction. Okay. Balance is quite simple, but nothing's going to happen. So there you go. Na metal, plain sodium, chlorine gas, Cl2. This is just going to be a two things you could call it. You could call this a synthesis reaction. Synthesis, meaning or composition. But in reality, this is actually a redox reaction. You'll see why. So it's going to make Na plus Cl minus. So we're going from a no charge and a no charge to a plus 1 and a minus 1. So, and I'll balance it quickly here, put a 2 here and a 2 here. And therefore, this is actually a form of a redox reaction. Alright. No voltage required on that one. So this is one where, actually, here's the voltage in case you want them. Would be 2.71, 1.36, give us a whopping 4.7 volts. 4.07 volts. So this thing is really giving it as far as voltage is concerned. Very violent reaction. Alright, this reaction is just a decomposition reaction. But it's also a form of a redox reaction. Doesn't really matter at this point. All we're going to do is we are going to decomposition. So they give you everything here. So this reaction is just an exercise in translating. So this is going to be PB parentheses NO3 2 goes to PBO plus NO2 plus O2. There's another example of a diatomic molecule here. Balancing wise, 2, 2, 4, 1. 2, 2, 4, 1. Alright, so magnesium metal. So magnesium metal plus, so once again, sulfuric acid, H2SO4. This single individual metal without a charge is a classic redox reaction. Redox. Okay, so the magnesium and the hydrogen are going to actually be exchanging electrons here. So the hydrogen is going to be all by itself. It's another example of a diatomic atom. Equals magnesium sulfate. These are both now +2 and -2. And no charge. So the half reactions here is magnesium going to -2 plus, and that's a 2.37 volts. And oddly enough, hydrogen H plus, which you'll find on your ion sheet, going to H, is 0 voltage and 0 volts. So 2.37 volts is what we got. Alright, keep moving along here. Keep her moving. Alright, so we got ethane. We have C2H6 plus a diatomic gas of O2 yields carbon dioxide plus water. You should probably be aware of these products anyways. We did this earlier in the year. But there we go. So this balancing wise is 2, 7, 4, 6. 2, 7, 4, and then 6. Alright, and that is a redox reaction, but we do not have any voltages for this one. The name for this would be combustion. Okay, so now we have chromium 3 chloride plus Au gold 3 sulfide. Put a 2 here and a 3 there. Now, again, we got a cation, an anion, cation, and anion. So solubility, in this case, no charges changing, just swap out to get potential new products. Chromium sulfide, which again is a 2 and a 3, plus gold chloride. Again, I recharge balanced to make sure everything was good, and it was the same as it was before. Okay, recharge balancing things. Okay, now again, probably the most common source of error for people is just not checking solubilities in here. So we have this guy forming a solid, and this guy forming an aqueous. Okay. All right, those are general reactions. Good examples of lots of stuff. All right, so what type of reaction is this? I have a cation, anion, cation, anion. This is going to be a solubility. All right, molecular equation is going to be barium chloride, 2 here, plus lead nitrate, all right, and then goes to my potential products are barium nitrate, and lead chloride, Pb, and then Cl2. Alright, so this guy is going to form an aqueous, and this guy will be a solid. This guy here, barium chloride, is somewhat soluble at different temperatures, so this ends up working out nicely, depending on temperature. But, so what do we got here? It's going to be ionic is barium plus 2 plus Cl minus yields, we don't yield, minus plus Pb2 plus NO3 minus yields barium 2 plus NO3 minus plus the last one PbCl2 I heap together because it is in fact a solid. And then we have here Pb2 plus, eliminating spectators, plus Cl minus, 2 of them, yields PbCl2. Alright, now let's draw this out. Now the ionic formula is really what represents the beaker below. So let's draw that out. It says how many we draw might be indicated here. It doesn't say. Alright, so we'll just do the same amount of each. Balance-wise, 2 chlorines, 2 chlorines. Looks like it works out. So I'm going to do 2 of each. Barium, I'll just do 1 of each. Plus 2 Cl minus, Cl minus. Lead, Pb2 plus. I'm going to use a negative for that nitrate. Negative equals NO3 minus. Alright, and then the lead and the chloride, that guy. Alright, put them together. This lead and this chloride reacts to form lead chloride, and therefore PbCl2. So I grabbed that guy, this guy, and this guy from that. Everything else is left. Pb2 plus, or barium, and then a nitrate and a nitrate. Alright. Spectators here just were aware the NO3 minus and the barium 2 plus are considered spectators. That's going to be something that is a pretty common question. Okay, now let's look at the drawing for a redox reaction. Alright, so what type of reaction is this? We got a solid chunk of aluminum is placed in zinc nitrate, so my molecular equation is just going to be aluminum plus Zn parentheses NO3 parentheses 2. And again, this is looking like a redox. You got aluminum nitrate plus zinc metal. Balancing wise, we gotta get this to balance out, 3 and a 2. So I'm gonna put a 2 here and a 3 there, 3 here, and a 2 here. Alright, so we're on this reaction. Net ion equation is going to be, now the best way to do this net ionic reaction, well, let's just draw it out. Aluminum metal plus zinc 2 plus NO3 minus yields aluminum plus 3 plus NO3 minus plus zinc metal. Alright. Determine the voltage process spontaneous. How do you know? Okay, so in this case, we have aluminum. I'm going to draw this thing towards the bottom here, the half reactions. So I have aluminum going to aluminum plus 3 plus my 3 electrons. And then I have my zinc 2 plus going to the zinc metal plus 2 electrons. And here we get that same ratio we had earlier when I balanced it. This whole thing times 2, this whole thing times 3 to get a multiple of 6 electrons. 6, 3, 3, 2, 2, and 6. That means my electrons have to cancel out on both sides. And I get my voltage on each one. Take a moment, check your voltages out. And we're going to get a positive 1.66 and a negative 0.76 for a grand total of positive 0.9 volts. So, is it spontaneous? How do you know? Yes. Why do we get that? Positive electropotential or voltage. Or positive voltage. Draw proportional particles of each process. Okay, so let's try this out here. To get this to run, I need to have 3 zincs and 2 aluminums is my ratio. So I have to have zinc 2 plus, zinc 2 plus, zinc 2 plus. All these guys are going to go up to the post, and then off jumps the post 2 aluminums. Aluminum plus 3 and aluminum plus 3. And I have my 3 zincs just sort of on the post 1, 2, and 3. These could be my zinc metals. Okay, they could fall off there too and land on the bottom, doesn't matter. How might the chemist, scientist, person speed up this reaction? Well, if you were to grind up the aluminum, you would get a much faster reaction. You could add a catalyst. You could increase the temperature of the process. You could increase the concentration of the zincs, 2 plus. You wouldn't be able to increase the concentration of aluminum because it's solid, but you could grind it up to get more surface area. So that's about it. Spectator ions here, just so you're aware, the zinc is the only spectator ion in this process. All right, thank you very much.